today we're going to talk about the Mandelbrot set in terms of the principle of incommensurability. Now, in the previous video, I said that the Mandelbrot fractal, the Mandelbrot set, is an embodiment of the principle of incommensurability. And so that is what I'm going to explain in this video. But first we need to do a review of complex numbers because complex numbers are also an embodiment of the principle of incommensurability. So as we all know, complex numbers are made up of real and imaginary numbers. Now historically, the way complex numbers are taught are a little bit maybe confusing to some people, especially people that aren't mathematicians, that don't process symbols well in terms of a symbolic language of algebra. And so what I did was I converted complex numbers to a 2x2 matrix, and these complex numbers are functionally identical to the original complex numbers. So the one thing I want to point out here is that although complex numbers can be represented in a 2x2 matrix, complex numbers are, for all intents and purposes, one number. So whatever is inside these brackets, inside the 2x2 matrix, whatever is inside these brackets, can be thought of as one number. One two-dimensional number. So this is a number, and I think this is what Eric Dollard was getting at in our conversation, was that, you know, we have to redefine our definition of numbers, and so, or something along that lines. And so, you know, this two-dimensional number, the two-dimensional complex number, which has a very specific rules, okay, and those rules are that the forward diagonal corresponds to the real component of the complex number, and they always have the same sense. So if this is positive, this is positive. If this is negative, this is negative. And the backward diagonal, which corresponds to the imaginary component of the complex number, always has the opposite sense. And so if one is positive, one is negative. If this is negative, then this is positive. But this is one, because of these rules actually bind the real and imaginary numbers into the complex numbers. So I don't want to have to use the terms real and imaginary, but since that is what mainstream uses, I'm going to continue to use those terms. But please don't take these words real and imaginary literally, because the forward diagonal and the backward diagonal of a complex number is, you know, are real and ponderable values. Well, I plug a value in here, 2.0, 1.5, minus 2.3, whatever numbers I plug in here are real and ponderable values. But the complex number itself, the 2x2 matrix, corresponds to one complex number. So when we look at the Mandelbrot set, you find that each complex number corresponds to a point on the complex plane. So on the left here is a representation, a map of the complex plane as iterated through the function z equals z squared plus c. This is the real component. So I put the real component on the y-axis when I render the Mandelbrot set. And I do this because I want you to see that the Mandelbrot set has very specific left to right symmetry. So this is the real axis. This is the imaginary axis. I put the imaginary axis on the x. It doesn't really matter which way you do it. If I rotate this 90 degrees counterclockwise, then you get, the mainstream orientation of the Mandelbrot set, which always puts this guy to the left. So this is, let's just have a look at the numbers here. So up here is -2 and 0. So -2 real, 0 imaginary. Down here is +2 and 0 imaginary. Over here is, let's just find the 0 point. So 0, 0. So 0, 0 is in here somewhere. 0, 0, 0 real, 0 imaginary is in here somewhere. This is -2 imaginary, and this is +2 imaginary. So this is the extents of the Mandelbrot set. The Mandelbrot set extends from -2 to +2 and -2 to +2. And so this is the complex plane. And so every point on the complex plane is responsible for a Julia set, which you are seeing on the right here. Okay, so each complex point, let's have a look at what it is here. So this complex point is minus 0.66 real and 0.54 imaginary, and this generates this Julia set here. So I'm just showing you all the features of the all the emanations of the Mandelbrot set, which you can see on this page here. You can see that, let's just go back to this one here. So the z equals z squared plus c as iterated through the complex numbers can generate this picture, can generate, so that's the Mandelbrot set, the Mandelbrot fractal, the Julia fractals, the Buddhabrot fractals, and the Bubblebrot fractal. And it can also generate these trajectories here. So each point on the complex plane, generates one of these guys. Wherever you are, you get some sort of trajectory. Now, when I plot lines, it's easier to see when I plot the lines between the trajectories. You can see that it is literally a trajectory such that, let me just zoom in a bit here so you can see it better. Okay, you can see that the lines are now connecting the dots. So when I don't draw the lines, I don't connect the dots, but when I do draw the lines, I do connect the dots, and you can see that they form a kind of trajectory. And the points on the inside behave different than the points on the outside, and that is the principle of incommensurability showing itself in the Mandelbrot set. So this was just a quick review of all the things that complex numbers can do when iterated through the function z equals z squared plus c. But in terms of the principle of incommensurability, let's just have a quick look at the definitions here. Okay, so incommensurability is having nothing in common, impossible to compare, or I like to use the word orthogonal. Now, orthogonal mathematically means 90 degrees out of phase or 90 degrees cross section. So basically, when you look at the Mandelbrot set, you see that the imaginary component, when you look at the complex plane, you see that the real component and the imaginary components are orthogonal. So this fits the definition, my definition of orthogonality. Okay, and so so let's go back to the definition. Now we'll talk about the conjugate nature. Conjugate nature is that they're joined together, especially in pairs. They are coupled, connected, and coexisting, and conceptually related. So all of these things are true of the complex numbers. Okay, so real numbers are not imaginary numbers, and imaginary numbers are not real numbers. And again, please don't take these words too literally. The forward diagonal numbers in the 2x2 matrix are not the same as the backward diagonal. The forward diagonal has the same sense in both of these quadrants, and the imaginary component has opposite sense in these quadrants. And so, but because of this, the forward diagonal and the backward diagonal can coexist in the 2x2 matrix. Okay, so they coexist. They are coupled. they're coupled by the expression. They're coupled by the rules. Okay, so the rules of the complex numbers in the 2x2 matrix format are that the forward diagonal are the same sense and the backward diagonal are the opposite sense. If I just put random numbers in here without these rules, then this would not be a complex number. So the complex number has these rules, and these rules bind the real and imaginary numbers into the 2x2 matrix in this form. And so the complex numbers themselves, in my mind, are an embodiment of the principle of incommensurability. Okay, so this is how I explain complex numbers. They can coexist in the same matrix, but real is not imaginary and imaginary is not real. And but they can coexist. They are coupled. Okay, they are joined together in the matrix, especially in pairs. So incommensurate principles always come in pairs. So real and imaginary numbers come together in a pair. It's very important that they work together. Okay, they're connected. They coexist. They can coexist in the matrix, and they are conceptually related because they form a number system. Okay, so that is the incommensurability of the complex number. So given that complex numbers are the embodiment of the principle of incommensurability, it shouldn't be too surprising to discover that the Mandelbrot fractal itself and all of its emanations are governed by the principle of incommensurability. So here is the Mandelbrot fractal. As you can see, there are two distinct regions in the Mandelbrot set, which I am calling incommensurate regions. I also refer to them as domains. So the points in this black region, what happens to these points when you iterate them through the function z equals z squared plus c is you get, I'm going to zoom in a bit here so you can see it better, you get a trajectory that collapses to singularity. Okay, it collapses to a singular point in the complex plane. At least the points in this region collapse to a single point in the complex plane. Okay, then when you go into these regions, you get different behaviors. Okay, so let me just have a look in here. So in here, what you get are 3 trajectories instead of 1 trajectory. But so all 3 of these trajectories, okay, all 1, 2, 3, these are also collapsing towards 3 singular points in the complex plane. Okay, but we'll just look at the ones in here for now. You can see that these points are clearly moving towards the smaller space, and this is what I refer to as counterspace. So to understand counterspace a little better, I'm going to show you what happens when you zoom in to the Mandelbrot set. Now, Eric Dollard says that describes space and counterspace in terms of a ruler. Okay, so he says that space is analogous to the ruler. So this is our ruler here. Our ruler are the extents of the complex plane that encapsulate the Mandelbrot set. So this is -2, +2, -2, +2. This is our ruler. Okay. Eric Dollard also says that counterspace is the space between the ticks on the ruler. Okay, the space between the ticks on the ruler. And so what are the ticks on the ruler in the Mandelbrot set? Well, the ticks on the ruler are the pixels. Okay, are the pixels. And so what I'm showing you here, so here I'm showing you the real and imaginary component of the approximate center of the image that you're seeing, and I'm also showing you the dimensionality of the pixel, the size of the pixel relative to to the big size. So the big size is 4.0 in the complex plane. This is a radius of 2 all the way around. So this is this measures 4. Okay, and so each pixel is 0.007812, you know, dimensions. So this is not, I can't say millimeters, but let's pretend they're millimeters. So if the width of this is 4 millimeters, then each pixel is 0.0078125 millimeters. And so what I'm going to do is I'm going to zoom in. I'm going to zoom in here because I like the way it looks, and it renders much faster. And so you'll notice that as I zoom in, the ruler, the pixel dimensions, get smaller and smaller and smaller and smaller. And so what I'm doing here is I am zooming into the Mandelbrot set, the Mandelbrot fractal, counterspatially. So the ticks on the ruler are getting smaller and smaller and smaller and smaller for every click, for every zoom in. Now I think I'm doing a 3 times zoom, so every time I click, it zooms in by a factor of 3. Okay, so I'm going to zoom in, zoom in, zoom in, and what I have here is 17 digits of precision. Okay, that is all that my computer can do at this point. Okay, so that's why I'm only showing 17 digits of precision. So I'm going to zoom, 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 and now you can see I'm starting to run out of digits. Zoom, 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 zoom. Now I've run out of digits. And so you can see what happens when I run out of digits. Now I have 0 digits of precision. I've got no digits left. And I also cannot render the Mandelbrot set. So my computer ran out of digits, okay? My computer ran out of digits. And that is why it looks funny. That's why it looks like this. So, but the point I want to make, I'm going to zoom back out. As I zoom back out, I'm always showing the previous step here just for fun, and zoom back in. So now when I zoom back out, I get my digits back and I can render the Mandelbrot fractal. So what I'm doing when I'm zooming in to the Mandelbrot set is I am zooming into Counterspace. Okay, I'm zooming into Counterspace. So Counterspace isn't nothing. Counterspace isn't non-spatial. Okay, counterspace is the space between the pixels in my image, or the space between the ticks on the ruler, which basically gets smaller and smaller as I zoom in to the fractal pattern. So fractal geometry really helped me understand counterspace. When Eric Dollard said, you know, space is the ruler and counterspace is the ticks between the ruler, I knew exactly what he meant. Because I understood fractal geometry, I understood exactly what he meant. Okay, counterspace need not be nothing. Counterspace is rich. In fractal geometry, counterspace is rich. Okay, it's rich with structure. It's rich with information. Okay, information can be stored in counterspace. Okay, information can be stored in counterspace. And so this is, I believe, what Eric Dollard was getting at, what Ken Wheeler is getting at, and this is definitely what I'm getting at. And so understanding fractal geometry was very helpful in me understanding the concept of counterspace. So it is my opinion that fractal geometry is the key to understanding counterspace. But not only that, it is the key to understanding the interface between space and counterspace. Okay, so counterspace isn't one thing and space another thing. Okay, the principle of incommensurability tells me that space and counterspace must coexist. Okay, they coexist. And so you're not going to find counterspace without a spatial component, and you're not going to find space without a counterspatial component. Say these two come together, they According to the definition, they are joined together in pairs, space and counter space. They are coupled, connected, and conceptually related. So I'm going to leave it at that for now. The main purpose of this video was to give you a better sense of this term counter space, which I've seen, many people find it a little bit confusing. They, maybe are misunderstanding it. So I wanted to use fractal geometry as a way of putting counter space into perspective. And so that, hopefully that is what I've done. And I'm just going to leave it at that and let you ponder the concept of counter space.